so far, when we've been talking about Newton's laws, we've broken these problems down into two types. Right? One's where there's an acceleration and one where there's not. And we've made a pretty big distinction about the importance of acceleration as a part of the problem. So if there is an unbalanced force acting in a system, the system changes. Now those changes we've made have been largely about if the object sped up or slowed down. And this is what we would consider acceleration. How much did the speed change? Now, that works great for one-dimensional problems, but there's quite a few examples when you don't want to travel in one dimension, where you would like to maybe make a turn and go somewhere else. Acceleration isn't just about how much your speed changes, but that's all we've really talked about so far. So we need to add into this not just changes in speed, but what happens when we have changes in direction. When we start talking about changes in direction, we're still talking about acceleration. An acceleration that causes a change in direction is still an acceleration and still is part of Newton's second law. Still going to be measured in meters per second squared, all of those things. However, this is not going to be adequate at calculating how you deal with an acceleration that changes direction and not speed, because the v part of that might stay the same. Imagine this, if you will. Let me try and draw this carefully. So we're looking top down on a car as it travels along a curved roadway. It's marked that the roadway has a speed limit of 35 miles an hour, so the car tries to maintain a constant speed. So trying to make all my arrows the same size. So there's the car traveling at a constant speed. I've picked 3 places on the road. So if it's traveling at 35 miles an hour the whole time, we wouldn't be able to use this to figure out what the acceleration is, now would we? Go ahead. That's it? Okay. Hardly seemed worth the trip. But we're good now. So, how is it that we figure out what's happening here? Clearly the car is accelerating. It's changing direction. But I want to look at the kind of the little nuance here. And I want to use some vocabulary that you may not know. For example, the road surface. There's clearly a curvature to the road. Would you agree? And I tried to make it look like that curvature remained the same the whole time. Do those 3 red arrows all look about the same length? We would call that the radius of curvature. I know some of you kind of think that we only deal with a radius if you have a full circle, but very few streets are a full circle. You know, there's turnabouts and stuff, sure, but usually if you have a well-constructed street and it has to make a turn or a bend, they attempt to make the radius of curvature of the bend uniform. It's easier to drive on when it is. Now, that's not South Mobley, which is clearly just a mess. But most roads, when they have to bend, they try to have a uniform, consistent radius of curvature, which also suggests that any curve in a road will also have a center of curvature. It's not a full circle, mind you, but it's a small segment of a circle. And you guys remember segments and sectors and arc lengths and all that from geometry, don't you? Totally. Yeah, that's not been the takeaway all day today, but let's just say that 7th period probably remembers everything.
Yes.
Sure, why not? Now, this part's going to be tough, but just bear with me for a minute. If we zoom in on one car for just a second, not like that. Not like that. Why is the zoomie not working the way I want it to? There we go. Let's try that. We look at just this car for just a minute. When you step on the gas or step on the brake, you're applying an acceleration either in the direction the car's already going, or you're applying an acceleration against the direction the car's going. You're making the velocity a bigger number or a smaller number. If you want to turn, then you're trying to do something completely different. If you're trying to turn, then you're trying to make this change direction without changing its size. The only way you can do that is if the acceleration has no component in the direction of motion. Being very careful about my word choice here, and I'm talking nice and slow so you have plenty of time to write these things down. So I'll say it again. If I want to speed up or slow down, then the acceleration is in the direction of motion or against the direction of motion. But if I want to turn, then I want to make sure that I have a component of acceleration that has no part in the direction of motion. Otherwise, I'll speed up my car or slow down. So if my acceleration's this way, there's a part of that acceleration that is in the direction of motion. That part would be causing the car to speed up. And if I have an acceleration that's like this way, well, there's going to be a part of that acceleration that's against the direction of motion. That's going to be causing the car to slow down. If I just want to change the direction of the car, then I need an acceleration that is perpendicular to the velocity. Now, if you look at all of the arrows of the cars, do you notice that all the arrows of the cars look like they're tangent to the path? Do you see that? The velocities are all tangent to the circle. It's not accidental. Whenever you travel on a curved path, your velocity at any point is tangent to the path. That's always true. You may not know that, but it's always true. In the case of these examples, if all I want to do is change the direction of the car, then I need to have an acceleration that is perpendicular to the velocity. And you may not get the result of this, but I'll say it clearly. If the velocity is tangent to the curve and the acceleration is perpendicular to the velocity, then this is the part you write down. Then the acceleration has to point towards the center of the circle. If you want to just turn and not change speed, your acceleration has to point towards the center of the curve. Again, if you want to change direction and not change speed, then your acceleration has to point towards the direction, towards the center of the circle. So we have a special name for this, of course. We call this centripetal acceleration. Center pointing, centripetal. It means center pointing acceleration. Now, this kind of acceleration, centripetal, isn't calculated by looking at how the speed changes. Instead, it's a combination of two factors: how fast you're going and the radius of curvature. Now, this is a little different than what we've talked about in the past. And I'll say it again, the whole point here is we're trying to change direction. So this has implications that might not be obvious, and I would like to kind of make them obvious. This is clearly how fast you're going. So I want you to think the turn between Sheldon and Citrus Park Boulevard. That left turn there, like you're leaving school and you want to go that way. They've added an extra lane now. But that's a hard turn to make because it's more than 90 degrees. And so if you watch how people travel in that turn, be careful. Some people hit it trying to make the light. And when they do, they start having trouble. Because if they start increasing how fast they're going, you realize this number is squared. This is how much acceleration will be required to make the turn. Something has to cause that. Worse, this is how tight the turn is. So if you want to turn sharper, it takes more acceleration, or you have to slow down. If you want to turn faster, it's going to take more acceleration, or you have to make your turn bigger. Those are your choices. You can't both turn fast and sharp and assume your car is going to have enough acceleration to do so. Because although when you think about acceleration with your car, you tend to think about something the engine is doing. But something has to cause your car to turn. Now, I'm bringing this up, and I'm trying to be very slow and diplomatic because of where we have to go next. We are not adding an extra force here. There's no new force being introduced here. Something has to be unbalanced to cause your car to have an acceleration. You need to unbalance the forces. There's not a new force. And I want to impress upon you that there's some vocabulary words that you guys might use that are wrong to use here. So who's heard of a centrifuge or centrifugal force or centrifugal force? A lot of people have heard these things and associated with going in a circle. So has anybody ever been on, say, the teacup ride at Magic Kingdom? Who's been fortunate enough to have to be stuck in the back seat with their siblings and maybe be the one that's in the middle, and then your parents make that turn and you all try and slam your brother into the door? Have we had that experience before? That's right. That's the fun times of being the older sibling, because there might be 3 of you back there. You make the turn, and it's the job of these two to shove this sucker into the doorway, right? Doesn't work the other way. You can't shove this way, can you? Not if you're making a left turn like this. And you'd wait for just the right moment so everybody slams their butt to the side and gets some. Or you have something on your dash here, and it looks like it's going this way if you make the turn fast enough. It's not. What's actually happening is it's going in a straight line. This line, the blue line. But your car is attached to the ground. And because your car is attached to the ground, after a few moments, it will be here. Well, now that thing has slid to there because that's where it wants to go. It wants to travel in a straight line. But you are in the car. You are driving. So you see the thing on your dashboard start to slide to the side. And the reason is everything in the car is attached to the car except for that thing that's laying on the dash. Something had to cause the object to have an acceleration this way, or it travels in a straight line. And the only way you can get something to accelerate is if there's an unbalanced force acting on it. So that's what it is. You're in your car, everything that's in your car is traveling with you. So you feel like it's not moving relative to you, but the car is. The car's changing. So let's talk about the car for just a minute. And it's hard to draw the forces on the car here. So I'm going to draw the car from the back. And I say that loosely because what I've been drawing today have not been cars. I have failed in the drawing of cars.
Looks pretty good to me.
Just wait, there's time. So these are the tires. And so this would be like the back bumper. Ooh, that didn't go well.
Are bumpers on cars made for crashes?
They're made to bump it.
I know, but like, are they made to be a cushion for crashes?
Yes.
Really?
In a day or so, we're going to talk about car crashes and seat belts and airbags and such.
It's kind of like the thing where like the sky. If you hit tree branches,
It, like,
slow
lets you
you.
fall.
It'll slow you. Yeah.
Yeah, 'cause it's like
There, is that like the back of a car?
Yeah.
Let me put some mirrors on it.
Now it's a cat.
Now it's a cow.
Why is he cute?
Stop it. It's a car. This is the that's the car thing. That's the license plate, and these are the rear lights.
Did you buy like the special 50?
Oh, the trunk. Well, this is the opening to the trunk. There.
Car distribution system.
All right, shut up, all of you. You're not. You're shaming me. Sure, it's a station wagon. So, name a force acting on the car. Good. Glad we get gravity. It's nice to get that one out of the way. Is the car in contact with any surface? So, that would have to be what kind of force? Normal force. Excellent. I assume those are balanced because the car's not accelerating upwards or accelerating downwards. So, what force pushes the car to the left? There has to be an unbalanced force to the left. What? It's got to be friction. It's got to be friction. The car has to have an unbalanced force. We want to prevent the car from sliding across the ground. I know many of you don't think that, but the car, you turned the wheels and then drove the car forwards. So there is a force against the wheels from the ground. Part of that force is trying to slow the car down, which is why you have to increase the speed of the car, increase the engine to maintain your speed. But the other part of that's causing the car to go this way. It's friction. In fact, it's not just any friction. It's got to be static friction that is causing this, because you don't want the tires to be sliding with respect to the car. Respect to the ground. There must be an unbalanced force, and it's going to be one of the forces we've talked about. Something, normal, weight, friction, tension, something causes your object to change direction. It's not a new force. There's no centripetal force. I will never say centripetal force. We will say that there's an unbalanced force causing a centripetal acceleration. That's what we have to say. And I need you to do more than this. I need you to realize that I'm going to take and make a coordinate system that is in the direction of the acceleration, which has to be, in this case, to the left, which as a consequence means the positive y direction is up and down. And from here, I'm going to say things like net force in the x direction equals MAC, explicitly indicating this is a centripetal acceleration, which means I'll say friction, which is in the x direction, equals mv squared over r. So we're going to have questions that you know are going to involve how fast can you go and how tight can the turn be. In the y direction, our net force is still 0. But normal minus weight equals 0. Nothing new, really, except for this one substitution because we're traveling in a circle. In fact, I move on with that to saying things like, well, I know static friction is equal to mu times the normal force. I can put these things together, start talking about how fast can I go. If the road is this sticky, what's the maximum speed limit before I slide? You guys following along okay? I know we think this is always about turning, but it's not. There's other examples of where this comes into play too. And I had a harder time convincing my other classes of this, so maybe I'll have a better time here. Who's ridden, let me just draw this first. Let's see if I can draw it maybe. Nope. So the Scorpion over at Busch Gardens is pretty old.
Yeah, it's closed.
it closed like in July.
All right, so pretty old. Obviously old enough for us to take it down. That's too bad. There was something fun you could do on the Scorpion that you couldn't do on other rides. And I'll give you some other things that we can do at the park that are like a little non-standard. But in the Scorpion, because of the way it was designed, you had no shoulder harness, but you still went upside down. And it's a neat experience because you could, because of the way the cars were set up, you could hold your hands underneath the lip of the car, so there wouldn't have been anything blowing against your hand. And you could put a quarter in the palm of your hand, and the quarter will stay there the whole time, even when you're upside down, to kind of prove to you that there's always a normal force acting on you when you're in the ride. Other rides, because of the way the cars are constructed, wind will just blow the quarter out of your hand, so you won't be able to see it. But you could do it in the Scorpion, which was fun. It was a neat little thing that you could do as a quick little experiment while you were there. But that's okay. There's bound to be plenty of other rides. But imagine as you come up to the top of this ride. Let's say that this is you already have some speed and you're going to make it up here, and then of course you're going to go down to here. Right, in these rides, we tend to not think about it, but the top of this ride is a circle. You're on a circular path right there. And clearly when you're at the bottom of the circle, that's a circle too. You're not making a turn, but the forces still have to be unbalanced in the direction of the circular path. So consider a simple roadway, something that you might drive on, where there's maybe a dip in the road, and then later on there's maybe a similar hill in the road, something like that. And you got your cruise control set, so you're staying at one common speed the whole time. Well, when you make it down to here in this roadway, if you want to travel in the circular path that's there, your forces have to be unbalanced. But you still just have the same forces, right? Weight downwards. In fact, if we just keep going with this, you know that you'll eventually make it to the top of the next hill, over here someplace. The weight of the car is not going to change between these 2 points, so the weight's going to stay the same, right? But when you're at the bottom, you need the forces to be unbalanced to get you out. You would prefer not to travel in a straight line, correct? And burrow into the ground. So the only way you travel in a curved path is if the upwards force is greater than a downward force. What's providing an upward force? It's still just the floor. It's the normal force. So if you're driving your car and you go through a dip, how many of you guys have ever been at the bottom of the dip and you feel that extra heavy right there at the bottom of the dip? That's the increase in normal force, pushing you up so you travel up out of the dip. If it didn't happen, you'd stay in a straight line. That's why you feel heavier for that minute. In fact, you can see it. You can just do the math on it. Net force equals MAC. This area must have some radius of curvature related to that particular portion of the road. And if you maintain your velocity, then, well, it looks like normal force minus weight equals m v squared over r, which means normal force equals mg plus m v squared over r. So clearly, the faster you go through that dip in the road, the heavier you're going to feel. Go ahead.
So part of the acceleration, you have to push on the gas mark, you're going to keep the same speed, right? So that's not just working against gravity, but it's also inevitably going to work against normal force as well, because if it's always perpendicular to the surface, at some point it's going to push you backward.
Well, yeah, but you're talking about, that's a change in speed that's going to occur, because you're going to go faster forwards or backwards. This is just...
But you have to increase, you have to push on the gas a little bit more to keep the same speed, because you're counteracting that, right?
Not if you have it on.
I see what you're saying. Only if your car was slowing down, right? If you're trying to maintain a speed, you wouldn't feel it. You know what I'm saying? You would increase the car's engine because it has to work harder because it's going to be traveling upwards. But this force wouldn't be from that. This force would just be from the ground. Okay? Now, you have the opposite effect when you go over the top of something. I mean, I'm kind of exaggerating this, but you know this part, the under, that feeling, but the over the top part feels like you're being flung out of your chair. Well, same thing's going to happen. The only force that can be pushing up on your car is the normal force. But in this situation, you need the forces to be unbalanced downwards. Because you want to not go in a straight line. You see that, right? If you go in a straight line, your car is no longer going over the hump. It's flying. The truth is it won't fly. It'll become a projectile. It'll have a parabolic path and it'll crash into the ground. So if you want to try and not be a projectile, normal force gets reduced, weight stays the same. This time, downwards is positive because you want to accelerate downwards. That's something small, but to put in your notes. We made upward positive here because we want to accelerate upwards, and we're going to make downward positive here because we want to accelerate downwards. So in that case, weight minus normal equals mv squared over r. Now I'm just going to solve this for the normal force, but normal force will equal mg minus mv squared over r. I know you guys don't like math so much and you get all nervous about the math, but you need to look and see what that says. This says that as I go faster, the normal force gets smaller. You see that, right? Because mg ain't changing. Do you also see that you could go perhaps fast enough where you make the normal force 0? Right? If you match it up just right, that means that's the speed where your car leaves the ground. If you go faster than that, the normal force has to be negative. Can the normal force pull down on your car? I mean, the street can't grab it and pull down. A roller coaster could. Roller coaster has wheels that are on both the top and bottom of the track. So a roller coaster could do so. Anybody ride Gwazi before they changed it? The old one? It was a pretty rough ride, but it had several places where you could experience a normal force of nearly 0, where you felt like you were being thrown out of the cars. Most roller coasters don't do that. Most roller coasters give you a normal force the whole time. But the old style wooden ones, they would have you go over dips just like this to try and reduce the normal force to something small. And anybody who's ridden in the back of the bus has experienced this. Okay. I want to, how many of you have been on the carousel at the mall? Oh God, I don't want to get you started. No, I don't.
I didn't have it. Let's go upstairs.
Just go right now. That's what I do. You're never too old.
You're never too old.
But it's like $2.50.
And then you swim in the opposite
Wow.
direction.
It's so expensive. It used to be like 25 cents.
Okay.
It's like $2.50 now.
I spent all my money on just today.
All right. On the carousel?
All my money.
Saxophone. I got a new saxophone yesterday.
All right. All right, so consider this, consider 2 horsies. Horsey number 1, horsey number 2. Your parents take you there when you were little, put you and your brother on there, and they said, finally, a moment without my stupid kids. They sat on the bench, and they watched you go in a circle. Make sense? You guys, let's say it takes 4 seconds for the ride to go around. That's not fast. 1 1,000, 2 1,000, 3 1,000, 4 1,000.
Long ride.
Okay, let's say it takes 6 seconds for you to go around in a circle. There, is that better?
Sounds fun.
All right. Does person 1 or person 2 make it there first? Okay, so we all know that they're all attached to the same ride. It takes 6 seconds for both of them. All right, just making sure. Which one's going faster, person 1 or person 2? See, interesting, huh?
Two has less to travel.
Now, the ride has one angular speed. I want to say this first. The ride has an angular speed. And when I talk about angular speed, I'm talking about things like RPM. What's that stand for? Rotations per minute. RPS would be what? Rotations per second. This ride is making one rotation every 6 seconds. There's a symbol for angular speed. You're going to come to hate it because all of second semester we do lots of angular stuff. But it's just a fancy W, angular speed. That's a symbol for it. It's the lowercase Greek letter omega, which is a W with flare. But I hope this part is obvious. The person that is on the outside is traveling in a bigger circle than the person that's on the inside. And since it takes them the same amount of time, person 1 traveled farther than person 2. Does that make sense? So if you wanted to know how fast they are going, because we're talking about, remember, centripetal acceleration, v squared over r. If we want to know how fast they are going, well, v1 would be the size of that circle, 2 pi, maybe we'll call it r1. And maybe r2, so we can kind of differentiate these things. So person 1 is r1 over time, while person 2 is 2 pi r2 over time. Now, if you had to figure out how fast they're going. Now, we'll have to deal with angular speed too eventually. But you could probably tell that person 1 is going to be traveling faster, right? We got that part down? Now, the problem is centripetal acceleration isn't just about how fast, but also how big the circle is. It might not be obvious which person needs more acceleration. But keep in mind, the velocity is squared. So it's a bigger factor. So because the velocity is squared, person 1 will need more force or more acceleration than person 2. That's why they always tell you to put the littlest kids on the inside. They might not be able to hold on very much, but the bigger kids on the outside. So before we split, how about the big person version of that ride? Who's ever ridden one of these? The thingy. You know what I'm talking about? Like the UFO or the graviton. You're like stuck to the wall. Well, let's talk.
Bro, I was standing up one time.
And the floor drops out, right?
You can just stand perfectly.
So do you guys, we know what we're talking about, right? So what force, I mean, you're traveling in a circle, right? Name a force acting on the person. Gravity is the good one. Got to get that one in. That's one we all know about. Yay, down. All right, name another one. So how would I draw the normal force here? It has to be perpendicular gravity. It's got to be from the wall. Well, what do you think keeps you from sliding down the wall? It's got to be friction. That's right. It's what prevents one surface from sliding past another. So it's got to be static, yeah. So this is it. These are the forces. It is the normal force that pushes you into the turn. This is why you feel like you're being flung against the wall. It's because the wall's pushing on you to make you travel in a circle. Remember, from the top down, if that force doesn't exist, if this is you, you travel in your last straight line path unless the wall pushes on you. That's probably bad for you in the middle of the theme park, right? So if you want to travel in a circle, the wall pushes you this way so that you turn and go to there. And now you're traveling this way. That's your next straight line path. But yeah, net force equals ma. So it's like normal equals m v squared over r. And friction equals mg. Yeah, that's what I'm seeing here. And then, of course, you start putting this stuff together and you get, right? How fast do I have to make the ride go so I can be able to be suspended against the wall? That's right there. Now, look, the bell's about to ring.